So when we face an integration question, these are useful formula you can memorize. You can use it. So integral of x to the n is easy, right? It would be the antiderivative of x to the n, which is x to the n to the power of n plus 1, divided by the same numbers here. The power of x here will be in the denominator. And remember, n is not -1. Okay? Because in that case, when n is -1, we have this formula, which is natural log of absolute value of x. Derivative of e to the x is e to the x. So antiderivative of e to the x is itself. This is a formula for the power function b to the x. We can use logarithmic equations, properties, and prove it using inverse function. But we're not doing it right now. You can review it in Calc 1. Okay. B here is any number. So from now on, if you see this formula, you can use this form exactly and immediately. Okay. When B is equal to E, what do we have here? This guy becomes e to the x, right? And the denominator is natural log of e, which is 1. Makes sense, okay? Antiderivative of sine, yes. Sorry? E to the x, that is a specific case. When b is equal to e, then we have this, the third formula. But in general, it is this guy. This is the more general formula, okay? If you want to prove it, you can go back to Calc 1, review it. There's a section mentioning these in very details. Antiderivative of cosine give us negative sine. Oh, sine, and antiderivative of sine give us negative cosine. Derivative of tan give us secant square. Similarly, we have these formula. Cosecant square, antiderivative give us negative cos tangent, etc. And here, remember, antiderivative of secant, yeah, this is a very useful formula. Memorize this. In order to find this, yeah, review section 7.2 and inverse function, etc. Okay, and so many other things. Sine hyperbolic, similar to cosine. Yeah, you just have to spend more time on these equations. It's similar to sine and cosine, but you can review it yourself. Here, this term x squared plus a squared, if you define x to be a tan cosine, right? Substitute it here, you can find this formula. Similarly, this is radical sine of a squared minus x squared. Review section 7.3. You see how to deal with this. And 19 and 20, similar things. Okay. And here they summarize all the situation we may see. So sometimes we need to do some manipulation. And for example, if we see integral of sine x plus cosine x and then perfect square of these. So we don't have any formula about this sum, right? But we can always make it easier by expanding this perfect square, which gives us sine squared 2 times sine cosine and cosine squared. And then trig equations, properties. Sine squared will be 1 minus cosine of 2x, and they all multiply with 1/2, right? Double angle formula. And sine, cosine here, you can do substitution, right? Or you can change it to sine of 2x, which will be 2 sine cosine. Go back to the formula sheet I gave you. You see all these formula. But anyway, all these three guys will become a single function of sine or cosine of different angles. Take the inverse antiderivative, that is not difficult. Or sometimes we will face these terms. Looks complicated, right? But once we distribute it, it becomes a lot easier. And integral of a sum will be sum of integral, and each of them is easy. Okay. So before you solve any question, review all the situation it may happen and pick a good choice in your point of view to do it. So, or sometimes you may see tan over secant square. There are many ways to solve it, but one way is you can do it like rewrite the tangent, which will be sine theta divided cosine. And secant is 1 over cosine square. Secant is 1 over cosine, then secant square will be 1 over cosine square. Division of two fractions, it will be the multiplication of the first one with a reciprocal of the other one, which will be this guy, and simplify it. Okay? And the formula of trig functions here, right? It becomes a lot easier. So if we face an obvious substitution, then that is beautiful. So for example, here, if we see the integral of x divided by x squared minus 1 dx here, right? And if we define u to be x squared minus 1, we take derivative both sides with respect to x. It will give us the relation between the two variables, u and x, which is in this guy. So luckily, here, the terms x dx, it means that we can write x dx in terms of du, right? So we can substitute it here, and then the integral becomes a new integral in terms of x. This is undefined integral, so we don't have to change the limits, the bounds. But if it is a defined integral, we need to find the relation between the two limits. In other words, if, for example, here integral from a to b, it means x runs from ba to b, right? When x is equal to a, then u will be a squared minus 1, right? Okay. Review the section 5.5. Or sometimes we may see these trig functions, then go back to section 7.2, sine, cosine, tangent, secant, etc., rational functions. So we may use some different substitution or integration by parts. Or if we see the radical signs, remember that we may use trig substitution here, which is given in the section 7.3. Review it. Okay. Sometimes the radical sign, it looks more ugly. Then we may define u to be the whole things here, right? Then if we define u to be this guy, so what is the relation between u and x here? right? If u to be the n root of ax plus b, then we take derivative both sides with respect to x here. The left-hand side is u prime, which is du over dx. The right-hand side will be this term, derivative of this term, right? And this root function, we can write it as ax plus b to the 1 over n, okay? And the chain rule, what do we have here? You can take a look at the formulas I gave you. But remember, x to the n derivative will be n x to the n minus 1, right? Or in general, if this is a function, u, don't be confused between these two u, okay? It will be u n to the u to the n minus 1 and multiply with u prime, okay? In our case here, it is ax plus b to the 1 over n. 1 over n is simply a number, right? So we can apply the chain rule using this formula here. Sounds good. Well, let me write it slowly here. And then let me write it down. It's easier to see. Thank you, Victoria. So, okay, in this case, u will be ax plus b here, right? So the power, we put it down, it would be 1 over n, ax plus b to the 1 over n minus 1, multiply with u prime, which is ax plus b prime here, right? Very good. Then 1 over n is 1 over n. And here, ax plus b to the 1 over n minus 1, right? And here, the last term becomes what? Yes, simply a. Thank you. So is it clear? So by doing that, our integration maybe becomes easier. Very good. Good job. Sometimes we need to do strict substitution, right? And sometimes it is really hard. And we need to manipulate the integrand here, for example. Integral of 1 over 1 minus cosine x. We don't see any formula like this. And here, the denominator is a subtraction, right? It's a lot harder. So imagine there's a number 1 here, right? And this term, the integrand here, it will multiply by 1 is the same, right? Or in other words, we multiply by this fraction. There's nothing changed, right? It's the same as multiplying by 1, okay? But then doing this, the denominator becomes 1 minus cosine squared, okay? And the numerator is 1 plus cosine. Using trig identity, we can simplify the denominator, which becomes sine squared. Then we separate this fraction, right? It will be integral of 1 over sine squared. Let me write it down. So we break this guy into two terms, 1 over sine square x dx, or let us write it this way, cosine x over secant of sine square dx, right? 1 over sine is cosecant. 1 over sine square is cosecant square. Okay? Cosine secant over sine square. Then from here, what can we do? The first one, is there any formula that we can use? There's one, right? It is the formula. Very good. Here, right? The second one, here, what can we solve the second one here? How can we solve it? Louder, please. Wow, very fast. I'm not sure about that formula, but sounds good. Or that is one way, right? Yep, it is somewhere here. Cosecant, cotangent, right here. Negative secant, very good. Good job. Or you can do substitution, right? If you define u is sine x, then du will be cosine x dx, right? So if we do so, then we can substitute this guy by du. It will be du over u squared, right? And again, we can solve it easily. Okay? This chapter is an overview chapter. Think, memorize, and master your skill, because there's nothing new. You've done all these kinds already. So sometimes yeah, dealing with this equation, this integral is tricky, right? And this guy, I've sent you in the group chat. Okay, we can do integration by parts. It's hard, but you cannot understand and or memorize it. Just redo it. Okay, you'll feel better, a lot better. Or if we face this guy, then review the section 7.2, right? And see how you can define do substitution using trig functions. Okay. Okay, that is a general idea of the whole chapter. There's nothing new. Okay. Okay, let us do these problems together. Example 1 here. Tan cube over cosecant cube dx. Tell me what you think and what we can do according to your point of view. So we will do it together.
Could you make it sine cube x over cosine cube x and then cancel out?
Let's try. It's a good point. Thank you, David. Let's try is your suggestion. Tan cube, which is sine cube divided by cosine cube x, right? And then the whole thing's here divided by cosecant or cosine cube dx. Be careful with the way you write the fractions here. It confuses. It is totally different from this one. Be careful with the way you write the fraction, okay? Be careful. Because here on the right-hand side, cosecant over a cosine cube over cosine cube give us 1. And in the end, it would be sine cube only, okay? But the true things here in this problem should be, this is a fraction, right? On top, divided by the whole number here, which is the division. We can write it as a multiplication. And reciprocal of cosine cube here will be 1 over cosine cube dx, okay? Do you see how tricky it is? Is it clear? Then this guy, it becomes what? Oh, be careful. The denominator, the numerator becomes sine cube times 1, which is still sine cube, right? But the denominator will be the product of cosine cube times cosine cube, which give us, yeah, cosine to the 6. This is multiplication. It will be cosine cube x multiply with cosine cube x, right? And it becomes cosine to the 6. If you do the sum, then it will be 2 cosine cube, which is totally different. Okay, careful. That is a good question anyway. So then we can write it integral of sine cube x here divided by cosine to the 6x dx. Okay. Now, do you have any idea how to solve it? Very good. We can do substitution, right? If we do substitution and we define u to be cosine x, then the relation between du's and dx will be very good. But here, it means that negative sine dx, sine x dx, we can write it in terms of negative du, right? Okay. And this guy, if we write it differently, is the same as sine square x sine x dx divided by the denominator here, right? Then if we do substitution, sine x dx here will be negative du, and sine square here, very good, it will be 1 minus cosine square time, let us rewrite it first. right? Now we do substitution. It becomes integral cosine x becomes u square here. Sine x dx becomes, be careful. Yeah, negative du. And the denominator is u to the 6th. Very good, right? Okay, then we get rid of the negative sign here, or we can write it u squared minus 1 du divided by u to the 6th, right? Do you agree? We take the negative 1 here, multiply with this term. And then what should we do?
Do something with the square on top.
We break it into two fractions. U squared divided by u to the 6th minus 1 over u to the 6th here, du, right? It's a lot easier. The first term, can we simplify it? Very good. Or we can write it u to the negative 6 here, and here is u to the negative 4, right? Writing it this way is a lot easier to find the antiderivative, which will be? Oh, be careful. Very good, yeah. Negative 4 plus 1 here, which is negative 3, right? Then divided by negative 3. Very good, thank you, Alu. And what else? Yes, a constant. Very good. Now let us simplify it. This guy becomes negative 1/3 of u to the negative 3, or we can write it 1 over u cubed, right? This guy, negative 1/5 here, give us plus 1/5, 1 to the u to the 5 plus c. Okay? Subtraction, negative of negative becomes positive. But we're looking for the antiderivative in terms of x, right? And here we define u is cosine of x, then we substitute back. It will be 1/3 of 1 over. Okay? Are we good? Good, very good. And, or another way. So let us go back to the original problems. We know that secant is 1 over cosine, right? So 1 over cosine cube will be secant cube here, right? Yeah, it becomes 10 cube x times secant cube x. And in the section 7.2, we know the strategy, right? 10 to the odd power here. So we can define u to be secant x and just apply the process. We would find another result, okay? That's it. There's nothing new in this chapter, but there are some more concepts. Okay. The what?
On the very last line.
Here?
Yeah, would you combine them?
Oh, we cannot combine because the denominator here is cube, cosine cube, here cosine to the 5th, right?
Okay.
Yeah, you, oh, well, I mean, I see. So you can write it as secant cube here, right? 1 over cosine, this guy, this guy is secant to the 5th, very good. Yeah, there are many ways to just manipulate it. Very good. So, and in order to answer this question, so the elementary functions are these functions: polynomial, rational functions, which is quotient of polynomials, power functions, which is x to the n or something like this, exponential functions, okay, logarithmic function, trigonometric, inverse of trigonometric functions, hyperbolic, inverse of hyperbolic, and all functions here with 5 operations: addition, subtraction, multiplication, division, and composite function. Then, for example, here, we're given this function fx here. Square root of this guy, under the radical sign here is a radical function, right? So it's still an elementary function. And at a natural log of cosine hyperbolic of x, it is a composite function of natural log function and hyperbolic function. Here is still an elementary function. Subtract product of a polynomial with an exponential function. So it's still an elementary function. So for elementary functions, the first derivative of these will also be an elementary function. However, integral of these may not be elementary function. Okay? And these are some more examples. You can read the book yourself. Okay? But now let us take the second quiz. So we have 15 minutes.
No, it's not.
There's no class after our class, so we can write.